All right, I think we're live. It is my absolute pleasure to be able to introduce ML Systems Seminar number 100, and we are very lucky to have here today with us Jared Dunnmon, who is the Senior Advisor for Strategic Initiatives at the Defense Innovation Unit. It's also a delight to be able to welcome him back, as he is a former postdoc from the lab Hazy that we are hailing from. And so he's going to be telling us a little bit today about how to apply AI in government, what's good about it, what are the problems, and I am very much looking forward to hearing. So with that, Jared, take it away.
Hey, thanks for the intro. I appreciate it. And thanks, folks, for tuning in today. I'll just kind of share my screen real quick. And then what I'll start with today is a couple of different things. I'll give you all a sense of what the different challenges and exciting pieces of working in the public sector are, specifically with AI in mind. I kind of previous to my current role, I ran that AI portfolio at DIU as the technical director. And so in that time, I've seen probably 30 to 40 different programs in the government specifically focused on AI. And I'll give you some high level thoughts. And then what I'll also do is dive into a specific program that I ran that in various ways will elucidate some of those specific items that I'll give you, in the front matter. And then would love to take folks' questions. I will preface this by saying that this time I've spent working in the public sector has been some of the most rewarding in my time. And for anyone who's interested, my email will be on the last slide. You are welcome to reach out and happy to help you think about that. So to start with, the high level thoughts I promised you. First of all, the public sector is a microcosm of society. And as such, it has a really, really rich problem space. Where I sat in the Department of Defense, you have to provide healthcare. You have to run financial systems. You have to analyze really big documents. You have to optimize logistics. You have to analyze huge amounts of data from an enormous variety of sensors. All of those things have their own particular problem sets, their own types of approaches and subtasks on which you might use AI systems. And so that's an exciting piece. And you might think that when you go into government, well, hey, these governments are really big organizations. They've been around for a really long time. They have a ton of data I can work with, and this is going to be great. Now, that last part is often true. It is going to be great. But the data can be just as hard as it is in the private sector, and sometimes harder. Because what you don't necessarily think about, or at least I didn't when I started, was a lot of times the data that you want is in a bunch of different storage systems. It's not necessarily searchable. It is maybe in running on a system that existed before you were born, with an ontology that's outdated, with words you don't know in it. And as a result, you've got to do a bunch of hard work to actually pull out the data from where it is, figure out if it's actually useful for the thing that you want to do, figure out if and how you can combine it with equivalent things from the private sector, and or take advantage of, say, models that were built in the private sector to transfer into data sets that have public sector characteristics. All of those things, I don't think anybody on here will be surprised when I say that data is some huge percent of the work for machine learning work. But it is just as true in the public sector. The amount of data, in fact, is often massive. You have the Veterans Affairs Administration in the US, for instance, probably has one of the best longitudinal data sets about human health that we have in the United States. But it is not necessarily always the easiest to start getting used to working with, or to access the various things that you want. So that's the data piece. On the public sector side, you also find that applications tend to lead access to hardware and software. So what you'll see is the private sector will build something that's really exciting. And then you'll say, wow, I wish I could use that in government. And then you'll realize, I need to go and get the right software. And then you realize, okay, well, that requires things like cybersecurity scans, like it would say in a corporate environment. That requires connectivity to the internet, which you don't have from every system in existence, depending on what it does. That also requires you sometimes to go buy it. And that can take a long time in the public sector. And then you realize, well, actually, I need hardware to run this on. And, I can't spin up, a bunch of GPU pods automatically. Like there are government cloud environments that exist that, where you can use some of the commercial cloud providers. But it's just the case that the compute is not always exactly where you want it. And so all of these things present engineering challenges, but also systems challenges. So for instance, yeah, I need to solve this problem in the private sector. I could just throw a silly amount of compute at it. For various reasons in the public sector, I can't. Maybe I need to run it on-prem for various security reasons. And so it presents you a different problem, and the trade-off space is different in an interesting way. But I'll also say that MLOps is a very persistent challenge. The ability to create many different models, for instance, and manage their deployment, and have the tools and the skill sets and the workforce necessary to do that is not something where the public sector is at today. The most public sector systems, and it actually was built over decades before most of the systems that we would talk about on this podcast would come into being. And as a result, you're working in a bit of a legacy environment sometimes, where the reality that software is a very living thing, and that you have to constantly update it as you do with, say, models that experience domain shift. It's not necessarily common practice. And so that's a consistent challenge that in the public sector you'll find when deploying ML systems. What I will also say, though, is like, as hard as some of these things and challenging as some of these things can be, there are use cases in the public sector that are just wildly interesting, and you either won't find them in the private sector, or they lead them by years, sometimes decades. And I'll give you one example that's I think pretty relatable. One of the programs that I spent a long time working on during my time in the DoD was focused on helping an unmanned underwater vehicle to do a mapping task. And if you think about an unmanned underwater vehicle, it has a limited power supply. And if you send it in fuel supply, if you send it off in the wrong direction, it actually costs you a lot. And so what you need to do is to be able to run a perception layer on a device that's power and compute constrained. And it's probably working off sensors that you're maybe not super used to. So, underwater, it's like, once in a while there are optical signals, but there's sonar, for instance, and sonar is a very different modality than the things that you would find in your normal machine learning papers. And so you've got to run models on new modalities that may be big, when you can't use a ton of power, and you also need to be able to monitor them on the edge, because it turns out that if I'm not talking to my autonomous my autonomous mapper for a long time, and it goes and it just decides that it's going to go off in the middle of nowhere somewhere, that I can't do much about it. And so imagine that I have a navigation system that's built on top of a machine learning based perception layer, and all of a sudden I end up in a world where I'm out of distribution from a training perspective, and I start getting a bunch of input that's wrong. My device can't just come up and say, hey, I see something wrong. You actually need to be running things like monitoring, or say embedding-based monitoring, or out of distribution detection on device, and link it in to system-mission autonomy. And that requires effectively a kind of an on-device performance monitoring regime or functionality. That's not something you necessarily always have to deal with in kind of commercial cloud deployments or in an academic setting. And so now you're actually starting to see commercial use cases for things like that. But when we started running that program maybe 4 or 5 years ago, most commercial companies you talk to would say, yeah, that's not really a situation we're designing for. And so there's these interesting situations where you're able in the public sector to do things because your problem set's slightly different that you don't necessarily find outside. And the last piece that I'll mention is that public sector AI is having a bit of a moment right now. I think folks in general understand that AI systems are going to have some impact on our society and the way that we run it. And we're trying to think about the ways in which they can help and do positive things, and the ways in which we want to ideally guard against negative outcomes. And we need folks who are fluent in the technical language of ML systems to spend time also getting fluent in the language of policy, in the subtleties of how we run our societies, whether in the US or not, because otherwise we're not going to make decisions that are as good as we could. And we have an opportunity to really get a lot of things right. So with that as context, let me give you a bit of a talk about a particular program that I ran that's very much out in the public domain. And it'll have aspects of a lot of these things that I mentioned. But what I also want you to take away from this is that in the public sector, when you build things, sometimes you build things in academia, sometimes you build things in commercial, and it doesn't, maybe it goes into a feature somewhere, maybe it goes into a paper. In the public sector, when you build something, the distribution you can get is, and the impact that you can have at scale is pretty massive. And so we'll get into what that looks like. The program, this is something that was done, as you can see, a lot of collaborators here, friends and including Ritwick, who was nice enough to let me use some of his slides for this. Ritwick, Fernando, who's over at with Global Fishing Watch, which is a nonprofit. We got folks from the Coast Guard. We got folks from NOAA. We got folks from the academic community. So all of the above contribute to these sorts of things. And in this case, what we were doing was trying to detect dark fishing activity using synthetic radar imagery. And I will now tell you what that means and why it's important, and why, from a ML systems perspective, it's actually pretty interesting. So as background, 1 in 5 fish caught around the world originate from illegal, unreported, and unregulated fishing. And this is combined with the fact that a huge percentage of the world's fish stocks are fully exploited, overexploited, depleted, et cetera. This is a massive economic problem. It is a massive environmental problem. It is a massive governance problem, because it is exacerbated by the fact that deep water fishing fleets often overfish in other countries' exclusive economic zones, which are, an area several miles outside of your border usually. And this causes all sorts of legal, ethical, economic problems. Now, the International Maritime Organization, the IMO, requires ships over about 300 gross tons of displacement, so just how much water the ship displaces, which is a measure of size, to be outfitted with what's called a automatic identification system. And that's a radio frequency signal that emits, "Hi, I'm ship X, and this is where I am, and broadly speaking, this is what I'm doing." If you're fishing illegally, or not where you're supposed to be, you tend to turn those off, because you don't tend to want to be broadcasting that you're somewhere you shouldn't be. Finding ships that are doing that is traditionally very difficult, because the ocean is enormous, and you never have enough vessels to patrol everywhere you want to patrol, particularly if you're a country that may not even have a coast guard. If you think about some of the countries out in the Pacific Island nations, these are countries with enormous exclusive economic zones on the ocean, but their ability to patrol those is very, very low compared to the amount of territory they have. And so, of late, with the revolution in space-based sensing and the revolutionary reduction in cost we've seen over maybe the last decade, you're starting to see not just electro-optical imagery from orbit, so things like cameras, but you're also starting to see things like space-based radar pop up, even in the open source. And that matters, because radar is a particularly useful modality for fighting this particular problem. So the way that this works is that you have a satellite. It's called synthetic aperture radar, usually, when you're talking about from orbit. And instead of having an enormous dish, which often governs how well you can receive a radar signal, what happens is you have an emitter that's on the satellite that's moving rather fast. And so it emits and then it receives. And then you can reconstruct a radar image from that looks something like this. And you'll note that it's reflectivity, not intensity. So the radar waves are actually scattering off of various things and coming back to you. There's a bunch of different weird types of artifacts that occur in this imagery that you won't find in electro-optical or kind of standard imagery that you would look at. And there's different polarizations to the electromagnetic waves that you care about. So we say VV and VH there. Those are actually different polarizations, and different things show up better in different polarizations. If you look here, this is a superimposed SAR image from Capella Space, which is a commercial satellite company, and an electro-optical image from Google Earth. And what you see is on the left, your standard camera image from orbit. And on the right, you see the SAR image. And you note things like metal lights up like a Christmas tree. But what this doesn't show you is that SAR, your space-based radar, is effectively impervious to cloud cover, to nighttime, to covering yourself with a blue tarp. And that is really, really important when you're trying to perform a persistent monitoring task like this. So what do? We actually, on the government side, spent a lot of time, built a partnership with some folks in the nonprofit world, particularly an organization called Global Fishing Watch, which does a lot of great work applying machine learning to monitor illegal fishing around the world. And we actually collected a large amount of open source SAR scenes. And it's some multimodal data that goes along with that. We then created an enormous number of annotations using a combination of automated means and manual means, and quality check these things and do all the things that you have to do to ensure data quality. And we ended up with something like 243,000 annotations and 82 million square kilometers of imagery. And yeah, I mean, we built a baseline model, and which was kind of a relatively simple, faster RCNN-based thing. But then what we did was we actually just released this out into the world and said, hey, can people please solve this? To give you an idea what's in that imagery, you see that things on the water in SAR look pretty interesting. So you'll have these patterns where you have very, very intense reflectors, and you get these kind of star-looking patterns. You can see ship wakes. If you look on the middle left, you'll see it's a wind farm, which is something where you're just a normal detector that was just detecting objects might say, oh, all of these are ships. Well, they're not. They're wind farms. You have artifacts like on the bottom row, particularly on the left. You see a couple of just radar artifacts. And so you even see some oil slicks, actually. So in this modality, the types of things that you have to do to handle the variation in the data and the types of things that you would do even for, say, data augmentation are very different than what you would do normally, and frankly can require some pretty complex simulators to do. So that data set, it was 991 scenes. Now these are big. These are each 20,000 pixels by 20,000 pixels, which is big, right? So that's a very, very large factor, larger than, say, an ImageNet image. You have things associated that are co-registered, like bathymetry, so how deep the water is, wind speed, wind direction, wind quality, a land or an ice mask. You co-register all these different channels, and you have your kind of 4 different partitions. You got a train and a validation and public leaderboard test set that you release, and you hold that one. You also have to do a lot in task design because you actually want people to kind of vector towards something that's useful to you. And so here we actually don't just care about detecting vessels, detecting objects. We care about, can you detect the objects? Sure. We care about, can you tell me how big it is? We care about, can you classify whether it's an object as a vessel or not? And can you characterize whether it's a fishing vessel or not? And oh, by the way, we really care if you're doing this well within 2 kilometers of the shoreline, because it turns out that when radar waves hit near the shoreline, they bounce and hit a bunch of different things, and it's actually kind of hard to figure out what's what. And so, but a lot of fishing occurs near shore, so we care a lot about it. So we have a metric that's pretty interesting. It's a weighted average of a bunch of different things. And on the public sector side, we're able to go get money for this stuff. And we put out prize money and say, hey, could people come and solve this? And we'll give you prize money. And obviously you can publish and stuff if you do. What's interesting about this is, again, it's not just a standard problem, right? There's a bunch of really interesting research problems that are inside something like this. So I'll give you an example. Long-range context over an image that is 20,000 by 20,000. So if I chip this image, like I would often do to say fit it on a standard GPU, I'm going to lose sometimes the long-range context, so I'm not careful. And I actually may care about that because imagine I see a little ship out in the middle of nowhere. That may not be that interesting. But if I see a bunch of little ships that look similar in a array around a bigger ship that starts to look like a mothership and a bunch of little ones out fishing, that I care about. And so that long range context is actually something I do care about substantially. And it's not necessarily the easiest thing from a systems perspective to analyze an image that large while maintaining reasonable levels of long range context and understanding what dependencies you care about and how to represent them. Another one is just the representation learning piece. It's very rare. It's certainly when we did this, and even now, to find just like a foundation model for SAR. It's also the fact that some of the data is even more complicated than you think. So the images I've been showing you are what's called GRD. They're post-processed into a radar image that you look at. The raw data you get is actually something that looks like it's called single look complex. So you actually have a magnitude image and a phase image. At a high level, physically, this is how much of my signal returned and how long did it take it to return. In that context, there's actually a lot more to do in terms of using the single look complex data and being able to handle some of the artifacts you see in the GRD data, maybe further upstream in the processing stream. These are all things that you could do. And so even with what we released here, which is pretty complicated from the standpoint of a data modality that folks aren't often used to working with, there's still more where that came from. And there's another piece here from a systems perspective that's really interesting, which is efficient inference. And it's not just efficient inference from the standpoint of, oh, I'd like to use a slightly smaller chip, and oh, I'd like to be, using less power or a smaller data center. This is fundamentally different. So I actually care about processing a huge amount of imagery that's coming down from actually many different satellite constellations. And most satellite constellations, particularly commercial ones, they won't record images over the open
Jared, we seem to have some kind of a bug on the audio. It's a little concerning. You try reconnecting. Jared, can you hear us? We cannot hear you at all. Discord, if you're hearing this too, please let me know. Okay, there we go. That seems better. Just stop for a moment.
Can you hear me now?
Yeah, we're back. Okay, I'm not sure what was up with that, but
okay. Do you know where I stopped?
Can you go back about probably 45 seconds before I stopped you? Yeah, it was on this slide. This slide is fine.
Okay. Perfect. Yeah. So just for folks who may not have heard, and I switched microphones, so tell me if it starts being weird. There's another interesting problem here in inference. And efficient inference is interesting here because you care about not just running, at a data center. When we run models that were submitted for this challenge, to start with, from a performance standpoint, the ones that were best were actually ensembles of a variety of different representations. And they actually took about 15 minutes to run over a full scene on V100. And that seems fine. But the big problem here is that what you actually want to do is process a huge amount of imagery that's coming in from space. And the bottleneck is actually not the compute. The bottleneck is communication down to the ground, to the point where most commercial satellite constellations won't actually record and store images they take over the open ocean because there just isn't a lot of economic value there. And so what you actually want to do is take these models and shrink them to the point where they still perform well, but you can actually put them on the satellite and you can be processing images to find things that are interesting and send only those things down. And so again, this is a problem set that you don't necessarily always find. There are some areas of kind of, your tiny ML world that care about these things. But you start caring about it in a very power restricted, a very compute restricted environment. And the thing that you also care about is
I need to get this thing down within, say, a couple of hours, because the quicker I get something down, the more actionable it is. And so I have to do some prioritization on what I send down as well. So these are where some of the systems problems actually lead to some operational impact. Just to give you a sense, like over time, we ended up with a lot of participation in these sorts of challenges. We had thousands of submissions from around the world, and performance did in fact go up over time, which was compelling. But what I'm going to get to now is actually what I think is one of the most exciting parts is, what do we do once we have a model that actually performs pretty well? Well, we actually were able to take it, wrap up the pre-processing pipeline. And I spent a lot of time with hands-on keyboard, which is fun. You can do that in government. And we deployed this thing to a system called CVision that is used by hundreds of countries around the world, by over 100 countries around the world, to view data about maritime domain awareness. So to view data that describes like what their oceans look like, et cetera, mostly for maritime security reasons. And what you see here is all the yellow dots on this view are vessels that were broadcasting AIS. And this is right off Chennai in India. And what you see here is a huge number of red dots. Those are SAR detections that are not correlated with an AIS signal that's known. And so these are all what you would call dark vessels. If you just looked at the AIS signal, you wouldn't know they were there. And there's a huge number of them, to the point where manual analysis of images that look like the one that I'm showing you, where there's kind of this little blob, it's hard, it's slow, it's unreliable, and it's frankly not feasible for most folks to do, particularly in areas where resourcing isn't as high as it might be in say the US or the Europe. And so, and you can imagine off of a place like Ecuador here, this is the Galapagos Islands, it's out there. Your patrolling assets are stretched if you're trying to keep folks from fishing illegally in the Galapagos Islands, which is a major problem that you can go read about. Now, if you look, this vessel that we've got here, this red dot, it's not very big. So a human might have missed that and probably would have. But you see this vessel sitting here. And so, what this allows you to do is keep an eye out for these sorts for incursion into marine protected areas. And even if you go and patrol in these areas once or twice, once you start to see, dark vessels showing up there, it can affect behavior. And so it allows you to get a major bang for your buck in terms of how do you deter the environmental and economic damage from illegal fishing, because you're able to use kind of ML combined with modern sensors, and that's deployed in a kind of a pretty efficient way. And there's a fun kind of way that we do the queuing and the inference to minimize costs, kind of on the from a deployment perspective, to be able to provide this for a pretty large number of countries at really, really low cost. These are things that just aren't possible with your traditional types of analysis techniques. So I'll end there by just saying a couple of things. One is to emphasize, you can publish when you're in the public sector. So this paper was actually in the NeurIPS Dataset and Benchmarks tract a year ago. Along with, again, all the authors here that put in a lot of work to do it. And I'll go back to those high-level thoughts, right? There's a really rich problem space in the public sector. Nearly everything that you care about in your community is likely something that at some point will interact with the public sector. And if so, there's likely a way that you can spend time working. The data is hard. Like I said, a huge amount of what I just showed you was just getting the data right and getting the ontology right and making sure that we were asking the right question and that we were designing the task correctly and the metric correctly. It's a lot of the grunt work of ML. But as always, that's where a lot of the value comes from. The applications here, the application was, hey, we want to address this issue of kind of illegal, unreported, and unregulated fishing, and we need to monitor it. We need to monitor it from satellites because that's the sensor we have. And so that leads some of the questions about software and hardware and efficient inference that I was bringing to the table here. From an MLOps perspective, it's still a challenge. Like we still have to constantly figure out a way to survey to make sure that our models are working right, to make sure that we update them at some reasonable frequency, to make sure that our bureaucratic processes don't get in the way of us doing that. All of those are still challenges. But again, this is a use case that there's certainly folks working on it in the NGO world, but this is what you would call a public sector use case, and it leads to a lot of very interesting kind of sub problems that whether you're a technical person or you're a very first person who's very interested in research or someone who's just really interested in building and deploying real systems, there's a lot of goodness and interestingness in there for folks to work on. And I'll just end by saying again that it's a really good time if this is interesting to folks, whether it's at the local level, at the state level, at the national level, international level, you name it. This is a really good time for folks with a technical background to get involved. And my email's there. If anyone's interested, feel free to shoot me a note. I'm happy to chat about any of it. So that's what I got for you today, and happy to answer questions.
Great, because we've got a lot. So some from the students, some from me. I'll start with a question that I was wondering a little bit about, which is that, I think perhaps the reputation of the government is that things move a little bit too slowly, a little bit too perhaps methodically. It's hard to get things done. And now that you've spent some time, I was wondering have you developed any tricks or learnings about, you should structure a project in this way if you actually want to push it through, or these kinds of things tend to work, these kinds of things don't work. How do you get things done in the public sector?
What I would say to this is, yes, things can move slowly because there is often in the public sector, there are a lot of equities involved. There are societal equities that are involved. There may be data privacy equities that are involved. There are a lot of different equities that are involved. And what I would say is folks who try to solve everything at once often end up getting frustrated. And so the two mechanisms that I've found for working with the public sector and within it tend to start in the following way. First, you have to understand who the stakeholders are and what problem they actually need solved. And the problem they need solved may actually not be the one they tell you they need solved. That requires getting out of the building. It requires sitting next to people, getting folks to walk you through what they're seeing, what problems they're having, and hypothesizing about how one can help. That's thing one. Thing two is there are often open source or non-government analogs to problems that the government has. So for instance, does the government have a lot more space-based radar than what the open source European Space Agency satellite data we use for this project? You better believe it. Is it necessarily a really high priority to go and exploit all that imagery for monitoring for illegal fishing, right? Versus say other use cases that are really, really important, not important, that are really, really high priority. Not always. So if you're trying to get say data released for something, or you're trying to get access to it, you're trying to get permissions for it, it can be a drag. And so what's often the best thing to do is to show something works on say an open source analog, and then say, hey, look, it works over here. So if y'all kind of turn the crank and make it such that we can work with a much larger version of this, we think that we can add value. That'll motivate people, and that'll align incentives. So I know it's not particularly satisfying, but a lot of it, what it comes down to is understanding what stakeholders' problems actually are, and then solving kind of a proof of value problem that will demonstrate to them the potential value that exists if you kind of unlock these heavier weight ways of working together.
Got it. That makes sense. There are quite a lot of student questions about security and privacy in working with the public sector. So yep. I'm going to sort of do my best to kind of lump a number of them that I think are similar together. But yeah, so on the whole, how does this vary kind of across different parts of the government? How do you think about it? And is this something that, you ever worry about when you're doing your work?
Yeah, I mean, certainly within my, the part of my life that I spent in the Department of Defense, it's a huge thing that comes up all the time. And in fact, one of the things that I spent my time doing in government, again, it's in the sense of what I hope is positive impact, right? Is I wrote, along with a couple of colleagues, one of the kind of initial DoD kind of documents describing how we address things like responsible use of AI. And one of the things that you have to do in kind of the thought process of working through that is think about do a harms analysis. Like, what are the things that could go wrong here? And how do I how do I either mitigate those, or do I decide that this actually isn't worth doing? We shouldn't do this for reason X, reason Y, reason Z. And certainly those are security issues and privacy issues. If folks have a chance to read, say, the recent executive order, some of the executive orders on AI, there's actually a lot in there. In the defense world, particularly in a US context, which is one that I can speak to, we actually put an enormous amount of effort into maintaining privacy and privacy and civil liberties in pretty much everything that we do. And that means that there are times where you have to do something in a way that is harder, because you are trying to maximize the probability that you are treating the data that exists and the the reach that the public sector has with the appropriate level of care. And in the US, I can tell you that the authorities that have to do with say collecting intelligence, for instance, they're very, very detailed and very subtle often, rules, regulations, authorities about what data you can use, how it has to be collected, et cetera, and so forth. And I think I'll say one of the things that I'm honestly proudest about, where ideally when our government's working well, we spend a huge amount of time actually trying to make sure that we're not using folks' data and information inappropriately. And so, if anything, what I would tell you is when you step into the public sector world, those problems probably become harder because of the amount of power that a government has. But for that reason, that's also why we need really sophisticated people to be thinking about how to extract value from the data and the ML systems that we can build, while still doing so in a way that aligns with kind of our values as a society.
Makes sense. One question I really liked was about to what degree one would want or be able to build human-in-the-loop pipelines in government. I think there's actually a very clear example for what it's worth in the example that you gave here, where you could flag something as an anomaly, but perhaps you can't be sure that it's a dark fishing vessel until you have someone go take a closer look. But I could imagine this for a variety of other reasons too. Do you have any experience with this?
Yeah, a lot. Because one of the big things, if you read some of particularly DoD policy on various types of systems, they will say things like, specific levels of human control, and they will specify in very, I don't want to say precise, I will say very carefully chosen language, exactly the level of human control that one would expect. And so, yeah, like in this case, there are a ton of use cases where you're just sorting through data and you're just trying to say, look, I have, a petabyte of images. Okay, there's no way that I as a human can sort through this petabyte of images. But if I can flag something with, forget the precision for a minute, forget the precision for a minute. If recall is reasonable, I can sort through a bunch of stuff that are like false positives, and I can find the things that are true positives as a human, and I can go in. And that's a pattern that tends to be pretty useful. There are systems where, honestly, like if I'm looking at like a back-end financial system and I'm just trying to say, I'm trying to learn how to do robotic process automation, I'm trying to do RPA, and the worst thing that can happen is just like the RPA fails. In those cases, you can actually automate things, but when you do, you have to do that harms analysis, which is okay, what can go wrong if this goes wrong? How am I monitoring for it? What's the long-term plan for checking performance? These sorts of things. So the short answer is that right now, the vast majority of systems that you would find in government, they are human-in-the-loop systems. Specifically for that reason, specifically because there are some equities for which we as a society are not comfortable delegating human control. Now, could that change over time? I'm sure society might change its mind on that over time. But right now, the vast majority of systems that you would find, if not all of them, are human-in-the-loop systems.
Great. Another student question that I quite liked was a question about sort of the division of AI work in government between the federal and state and local levels. And I will editorialize on this a little bit, that I think this is an interesting question too, because there is some natural balance of power between the different levels of government in the United States, at least. and that if only the federal government has lots of AI work, that potentially upsets that balance. So kind of curious what you think about it.
Yeah, it's a good question. I think there are a couple of pieces here. One is the regulation, and one is the actual work. The work itself, I mean, if you look at the arguments for, say, the National AI Research Resource, the whole point of that was that, hey, we actually need a centralized resource, in the same way that, say, national labs have supercomputing and whatever, so that folks across the country can actually do work at a very high level of computation, because it's not necessarily easy to agglomerate the amount of computation you need for modern research in various areas on one's own. That's thing one. So I think a lot of those things will continue to be like federally resourced, would be my guess. What you do see is a huge amount of state level regulation. Because actually, if you think about it at the national level, what you have is mostly executive orders, which can be repealed. They do not have the force of legislation. And what you're starting to see, right, is individual states putting forth a huge amount of AI regulation. At the same time, you're also starting to see bodies like the AI Safety Institute under the Department of Commerce at NIST, the National Institute for Standards and Technology, try to start to build out kind of a set of best practices and standards for AI deployments, right, and say in the commercial sector. And so what I expect is for there to be substantial amounts of federal work on this, because if you end up with a patchwork set of state regulations, it's going to be really hard to deploy software. I mean, right now it's like, what, I have to deploy software substantially differently in state X versus state Y versus state Z. Like in some cases that's a little bit true, but it's probably not an end state that's going to be really easy to deal with from an AI perspective. I do expect that there will be states that will have specific matters they care about. And again, you're starting to see it in a bunch of different US states where they will try to legislate. And my guess would be that for cases where the particular item that's being legislated is not that common, maybe it stays at the state level. But for things that start to affect, like, once you start affecting things like interstate commerce, like you end up dealing with a bunch of federal regulation. And so just because of that kind of fundamental fluidity, I would argue that a lot of it, even if it's motivated originally by state level legislation, would ultimately be encoded in national legislation, because otherwise, from an economic perspective, it's going to be a huge pain.
Got it. Maybe as sort of a follow-up to that, in terms of also divisions of how these things interact with each other, can you talk a little bit about the sort of how the private sector interacts with the public sector here, in terms of, like, do we see that kind of on the ascendancy, or is there just sort of so much more to pick in the private sector right now that the public sector is kind of being forgotten?
Yeah, well, as long as the public sector is spending trillions of dollars a year, the private sector is going to be interested. So the short version is that over time, the private sector, the closeness with which the private sector and the public sector are acting, I would argue is increasing. And that's not just in the US. And you see that, I would say you see that everywhere from China, where you've got substantial amounts of civil military fusion between the public sector and the private sector, to the point where in many ways the organizations are quite similar. On the US side and in Europe, you see, well, let me start there. In the US, you see companies starting to sell more to government customers than public sector customers, because there are efficiencies that we can get and cost savings that we can get from AI systems that are substantial, and that allow us to run our society better. And I've seen that from certainly the Department of Defense across a bunch of different applications. And again, I've said a bunch of them, but just to give you an idea, like everything from automating financial workflows to building augmented reality microscopes for the pathologists out in the Naval Medical Hospital at Guam, so they can like automatically read the number of slides they need to read, or get assisted reads. That's all happening, and the government and the government in the US is getting better. It's not good at it, but it's getting better at buying software. And so you're starting to see the wheels turn. What I'll tell you also, though, is that the regulatory environment is a huge effect. I mean, Europe is, I would say, if you look at the EU AI Act, you can make a reasonably good argument that Europe is kind of out in front on how far along they are in implementing or conceptualizing regulation and getting it through their regulatory bodies, their legislative bodies. But it remains to be seen whether the regulations that are put in place actually make it harder for the private sector to sell the public sector, depending on which jurisdiction you're in. And so a lot more of history is still to be written there, and it's a very, very interesting intersection. What I would tell you right now is the trend lines are towards closer work between the public and the private sector, just given the amount of benefits that the AI systems are already starting to show.
To follow up on that, I mean, most of what I see in the news about these sorts of partnerships tends to focus on really big companies, the Jedi contract or things like that.
Mhm.
Do you have any intuition on sort of what like how top heavy is this distribution? Is it really just, only the big companies that kind of know how to work with government and all the small players are left out? Or is there sort of becoming a thriving ecosystem of small entities that can actually go solve public problems?
So I didn't plant that question, but so my job for the last 3 or 4 years was exactly working on that, which is so the Defense Innovation Unit. What I focused on doing was running acquisition programs that were particularly amenable, that focused on getting non-traditional software vendors into the U.S. national security innovation base. So working with the U.S. government, and the way you do that is by making it such that there is a clear path to a very easy submission, a pretty rapid down selection, get them on a contract that looks like a paid proof of value very quickly. And then if they succeed at what they were aiming to do, provide a pretty clear path for acquisition at scale within the government. And what I just said sounds easy, but bureaucratically it's not, partially because in DoD, for example, the government budgets 3 years in advance. So if I budgeted 3 years in advance right now, ChatGPT hadn't happened when I wrote the budget for this year. And so you can see how that might change things. And so the thing that government actually really needs to get around to work with the private sector is being able to more rapidly budget for things and be able to more rapidly adjust its acquisition processes to test these hypotheses about where value is and then rapidly absorb them when it's possible. So, but there is a massive desire to do that, and change is happening. Again, I think over the last couple of years, I've seen, I've seen a couple of things. One is you'll probably transition nearly like 30 different vendors I can think of. There are small folks you wouldn't know. There are startups, maybe some of them you would know, so in the Valley and otherwise, that are working with the government, and they're working with them long term now. I've also tell you that the number of submissions that we've gotten as we put out solicitations for various things has gone up from we used to get like 30 per. I mean, it's in the hundreds per now. And so it is moving in that direction. And there's specific mechanisms that are aimed to enable smaller companies to work with the government, even if, and I will say this is important, they often need the big players' infrastructure to do the thing they're doing, right? So, if you're going to try and do all the cyber stuff yourself, you need to get inside a government network. That is a pain. It can be much easier to partner with, say, one of the CSPs who's done that already, get your stuff in the door, and then use that infrastructure to run your initial work, and then eventually move. So these big players are important partners from an infrastructure perspective, but I would say they're functioning pretty well as a bridge to enable small companies to work with the government better. So it's a whole ecosystem starting to work together.
Got it. That makes a lot of sense. And there's one final question from me that I'm wondering about is that, right now, most of my friends in the AI world are like very much focused on the private sector, perhaps because of money, as opposed to the public sector, which generally does not pay quite as much. What are your thoughts on how to get more great people into the public sector? Do we need to find ways to just make comp more, more similar, or do we have to find ways to leverage, patriotism, sense of duty, other things in order to get people involved?
Yeah, I didn't plant that one either. That's a very good question. And you're right. It is an unfortunate reality that is often economically irrational for AI practitioners to go work in the government. If you were to just look at the numbers, some of it is certainly a sense of mission. In the sense that when I get up every day when I'm working those jobs, like I know exactly why I'm doing what I'm doing. I'm working late in the evening, not because I have to, but because I want to. You're surrounded by people who have a similar mindset. And that's not always the easiest thing to find. If you're trying to hit, whatever, a particular OKR, you're like, all right, come on. I mean, how much do I care? The things that you work on in the public sector are often things where, they get you out of bed in the morning. And so that's thing one. Thing two is that I think you're going to see more and more often a healthy pattern of dual fluency talent that's moving back and forth between government and the private sector. So, I mean, that's what I'll be doing, right? So I'm I mean, I'm in the process of starting a company now, right? So like I spent my time in government and then learned a lot, ideally contributed a lot, and then I'll be back in the private sector for a little while. And there are various ways that even when you do that, you can keep your connectivity. So there are a lot of folks who are reservists, who are effectively part-time civil servants. There are folks who they're civilian equivalents, where you can do part-time civil service. So on some of the advisory boards, on kind of in a variety of capacities. And so I think it's less that you need folks to, and in a perfect world, would we make it such that it's less economically irrational to go work in the government? Yes. And there is progress being made towards that. But what the world likely looks like is less a matter of saying, hey, the government's going to exactly match private sector pay. Like that's probably not going to happen. It can get better, but it's not going to match it. The things that you're going to need to do is build a structure wherein when you have folks who are in the right kind of time in life, position in life, to go and spend time in government, it's easy for them to do it and then to go hop back out and then like hop back in later. And ultimately, that's the most productive way, because honestly, if you hop into government and stay there for 20 years, you're not going to know anything, but you're not going to be current by the time, right? By the time that you leave. So actually what you need to do is you need to there's an explore exploit trade-off, right? When you're in the private sector, you can be, you're in when you're, I guess, let me put it this way. When you're in the public sector and you've come from the private sector, you can be exploiting a lot on your private sector knowledge on the things that you know how to do and exploring a lot on like how the government works. When you leave, if the problem sets that you were working on in government are interesting to you, you can be doing the reverse. You're kind of diving back in from a deep technical perspective, and you're exploiting on all the things that like what the problems are, how what to go after, and you can be leveraging that in the way that you do your private sector work. And so there's a virtuous cycle here where if we build a bunch of dual fluency talent that can be doing that, that's how we're going to end up in a better spot, as a country, whether it's the U.S. or outside.
Makes a lot of sense. All right. Well, I think that's all I've got. So thank you so much for the talk. It was an absolute delight. Great to have you back. And let's say goodbye to YouTube.
Likewise. Thanks, folks.
Thanks.
Cool.
Okay, great.